Okay, so here's just a video since we're asynchronous today and you have a quiz. Here is me going over the homework that I would normally do live with you. So the number 11, I use limit comparison test. You can use the direct comparison test. It would work as well. As I mentioned before, generally, if I'm going to compare to a p-series, I use limit comparison. And if I'm going to compare to geometric, I generally use direct comparison. So that's no different right here. If you go through all of the tests, other than the comparison test, this doesn't fit into any of them. It's not exponential, so it's not geometric. It's not a p-series. It's not alternating. You can't use the nth term. It's not linear, so it's not arithmetic. And it's not doesn't have exponential or factorial, so I wouldn't choose ratio either. So it doesn't really fit into any of those other ones. That leads you to a comparison test. If you cover up the +2 and the 3, the constants, that's a p-series. That tells me that's what I want to compare it to. So what you're given is your a sub n, and cover up the constants, and I have what I'm going to compare it to, 1 over n squared, which is my b sub n. So I'm comparing it to a p-series where p is 2, so it converges because p is greater than 1. And then the limit comparison test, so I find what I'm going to compare it to. In this case, I state what that is and get a conclusion and why. Then for the limit comparison test, I find the limit as n goes into infinity of what I was given divided by what I'm comparing it to. So then I just rewrote it. Instead of this divided by that, it was this times that reciprocal, which gives you this. And the limit to infinity is a clear rule too. I get 1/3 as the limit. As long as that limit is positive and finite, whatever I said about b sub n, I'm going to say about the one I was given. So since I said b sub n converges, then I would say that the one I was given, a sub n, converges as well. So for number 12, I also use limit comparison because, again, I was comparing it to p-series. You cannot use direct comparison here. It fails. So again, if you cover up the constants, that's what you can compare it to. And 1 over n is a p-series where p is 1. If you try and make any of the other tests work for that, none of them do. So you're left with a comparison. So cover up your constants. I'm going to choose my b sub n as 1 over n. That is a p-series where p is equal to 1. If p is less than or equal to 1, it diverges. Okay, then I have to run my limit comparison test to see if I can also state that this function, a sub n, diverges. So my function I was given divided by what I'm comparing it to, rewrite that. It's this times this reciprocal, which gives you n over 2n minus 1. The limit is 1/2. As long as that limit is positive and finite, whatever you said about the comparing series, b sub n, you can say about your given series. So I can say that it diverges, it meets that condition. All right, number 13, ratio test. So the reason I'm going to use the ratio test is because not only does it have an exponential portion, 4 to the n, but it has n somewhere else as well. Okay, so the exponential usually makes me think about the geometric series, but then that n complicates it, and it's no longer just geometric. So that's what causes me to choose the ratio test. So if I use the ratio test, I need to create an a sub n plus 1. What I'm given is a sub n. So my a sub n plus 1, I add 1 to all the n. So it becomes n plus 1 over 4 to the n plus 1. The ratio test is the limit to infinity of the absolute value of the a sub n plus 1 function divided by the a sub n function. So again, the next step is to write it as multiplication instead of division. So it's this times this reciprocal. Here is where you can simplify using exponent rules. So if the bases are the same and you're dividing, you can subtract your exponents. We had the one similar in class, except the base was 2 and then the base was 3. So this reduces down to 1/4. So this becomes a 1 and this becomes a 4. And so this ends up being my fraction. And the limit to infinity for that is a rule 2, where the limit is 1/4. If the limit is less than 1, then my conclusion is that the series converges. For number 14, I'm comparing this to a geometric series, so I use direct comparison test. You could use the limit comparison test as well. Again, generally, if I'm using a comparison test and comparing it to a geometric series, generally we'll choose direct comparison test. So if I cover up this -1, okay, that -1 keeps it from really fitting in with any of the other tests. But as soon as I cover that up, it becomes a geometric series 3/2 to the n power. So my comparing function b sub n is 3/2 to the n power, which is geometric. R is 3/2, and the absolute value of that is greater than or equal to 1. So this geometric series diverges. So then remember that the test for direct comparison, when b sub n diverges, is that b sub n has to be between 0 and a sub n for all values of n. So I did n equals 1. So if I put n equals 1 here, I get 3/2. And if I put n equals 1 here, I get 3. 3/2 is smaller than 3, so that works. Then I tried it with 2, and that worked as well. Therefore, I can say, since my b sub n diverged, I can say that my given diverged as well. For 15, so I use limit comparison. You cannot use direct comparison. You can, but it'll fail, and then you have to use limit comparison. Nothing else really works for this, so you have to use comparison test. So what am I comparing it to? Cover up the constant. N over n squared is what I'm comparing it to. So that's my b sub n. That is really nothing as it is, but if I reduce it, it reduces to 1 over n, which is a p-series, 1 over n to a power, where p is 1. So p-series, p equals 1. Remember, it's p less than or equal to 1 causes it to diverge. So then for the limit comparison test, I did the limit as n goes to infinity of the given function divided by the comparing function. And then when you change that, you multiply by this reciprocal, you end up with this. And that limit is a rule 2, it equals 1. 1 is positive and finite, which is the condition that has to be met. So since I said b sub n diverges, I say that this one also diverges. For 16, I use limit comparison again. I tried the direct comparison, it fails, so you can't use that. Or you should also find out that fails, and then you continue with limit comparison. So for this one might have given you some trouble. It doesn't really fit into any of the other tests. Again, that's how we know it's a comparison test. So here you got to cover up a lot of stuff. Every other one, it was just constants. We didn't really cover up any variables. But here, to make it work, it's not going to compare to a geometric series because it's not exponential. These are polynomials. So you actually are going to cover up all of this. That's what's going to make it a p-series. I can't keep that in right there, that term, because then it won't be a p-series. P-series has to be 1 over n to some power. So I get rid of the +5, the -2n, and the +3. All that goes away, and I compare it to n over n cubed, which reduces to 1 over n squared. So that's a p-series where p equals 2. If p is greater than 1, it converges. Then I did my limit comparison test, the limit as n goes to infinity of what I was given divided by what I ended up comparing it to. So I changed it from this divided by this to this times this reciprocal. If you distribute it here, that gives you n cubed, which matches the n cubed on the bottom. So the limit is 1, which is positive and finite, which is the condition we were meeting. So since I said that my b sub n converged, I can say that this converged as well. For 17, you could use direct comparison or limit comparison. Again, I use limit comparison. That's one I prefer, especially if I compare it to a p-series. Again, if you kind of think through all the other tests, you'll kind of come up with nothing. So just like number 16, you're going to end up covering up that too. You have to make it look like a geometric series or a p-series, and it's not exponential, so you're not going to be able to make it look like a geometric series, and you can only make it look like a p-series if it's 1 over n to a power, so you have to get rid of that part. So you're going to compare it to 1 over n cubed, which is a p-series where p is equal to 3. If p is greater than 1, it converges. So then the limit comparison test is what you're given divided by what you're comparing it to, which ends up being n cubed over n cubed plus 2 and 3n squared. That's a rule 2 where the limit is 1. The condition is that that limit needs to be positive and finite, which it is. So since b sub n converged, I can say that this one converged. For number 18, so it's kind of a trick. You can use a comparison test, compare it to a p-series, but you can actually just simplify number 18. It's n to the 1/3 over n. If the bases are the same and you're dividing, you can subtract your exponents. So when you simplify number 18, the function you're given, it is a p-series. So you can actually just use the p-series test. P is 2/3. When p is less than or equal to 1, it diverges. So you can go through the steps for comparison tests, but you actually don't need to for 18. For number 19, I used ratio test. Again, it's got the exponential part, but then it's got n somewhere else as well. So when I do a comparison test and I compare it to a geometric series, it will have exponential, but then there'll just be like a constant or something. N squared is more than that. Okay, so that's why it's ratio test versus comparison test. So I'm going to use the ratio test. This is my a sub n. My a sub n plus 1 would be 2 to the n plus 1 over n plus 1 squared. And then the limit of this divided by what I was given. So then rewrite it as multiplication. You can reduce these two terms right here. The bases are the same, and we're dividing, so that's going to reduce down to 2 over 1 because you subtract the exponents. N plus 1 minus n just gives you 2 to the first power. So this becomes a 2 and that becomes a 1, so that this ends up being your expression or your function. The limit would be a rule 2 where the limit is 2 and 2 is greater than 1, so it diverges. And then for number 20, I use limit comparison test. If you multiply that denominator out, it's not exponential, so you're not going to compare it to a geometric series. If I multiply that bottom out, 2n squared plus 2n, it's going to be similar to 17. So you do want to like multiply it out to figure out that you're going to cover up the 2 and the 2n, and you're going to compare it to 1 over n squared, which is a p-series where p is 2. If p is greater than 1, it converges. So my limit comparison test is what I was given, which is this, where I covered up the 2 and the 2n, a lot like I did in 17 and in 16. And I compared it to 1 over n squared, which gives me this, and the limit there is 1/2. The condition is that the limit has to be positive and finite, which it is. So since my comparing series converged, I can say that the given series converged. Okay, that's it. Good luck on your quiz.